Control chart is one of the important tool of 7QC tools. To understand control chart and other problem-solving tool, we have to know SPC concepts in details. So today topic is Basic Statistical Concepts. Here we will discuss about different concepts and terms which are used during problem solving and SPC. Why do we need quality tools? As per Kaoru Ishikawa, as much as 95% of quality-related problems in the factory can be solved with 7 fundamental quantitative tools. Next is, what is quality processes? To attain quality, it is well to begin by establishing the vision for the organization along with policies and goals. Conversion of goals into results, making quality happen, is then done through managerial processes, sequences of activities that produce the intended results. Managing for quality makes extensive use of 3 such managerial processes: quality planning, quality control, quality improvement. These processes are now known as the Juran trilogy. In quality planning, first establish quality goals. Next, identify who the customers are. Next, determine the needs of the customers. Next, develop product features that respond to customers' needs. Next, develop processes able to produce the product features. Next, establish process controls, transfer the plans to the operating forces. In quality control, first, evaluate actual performance. Next, compare actual performance with quality goals. Next, act on the difference. In quality improvement, first prove the need. Next, establish the infrastructure. Next, identify the improvement projects. Next, establish project teams. Next, provide the teams with resources, training and motivation too. That means diagnose the causes, stimulate remedies, establish controls to hold the gains. Next is the Juran trilogy diagram. The 3 processes of the Juran trilogy are interrelated. The Juran trilogy diagram is a graph with time on the horizontal axis and cost of poor quality on the vertical axis. The initial activity is quality planning. The planners determine who the customers are and what their needs are. The planners then develop product and process designs to respond to those needs. Finally, the planners turn the plans over to the operating forces. You run the process, produce the product features, and meet the customer's needs. As operations proceed, it soon emerges that the process is unable to produce 100% good work. Figure shows that over 20% of the work must be redone due to quality deficiencies. This waste is chronic, it goes on and on. Why do we have this chronic waste? Because the operating process was planned that way. Under conventional responsibility patterns, the operating forces are unable to get rid of this planned chronic waste. What they can do is to carry out quality control to prevent things from getting worse. Figure also shows a sudden sporadic spike that has raised the defect level to over 40%. This spike resulted from some unplanned event such as a power failure, process breakdown, or human error. As a part of their job of quality control, the operating forces converge on the scene and take action to restore the status quo. This is often called corrective action, troubleshooting, putting out the fire, and so on. The end result is to restore the error level back to the planned chronic level of about 20%. The chart also shows that in due course the chronic waste was driven down to a level far below the original level. This gain came from the third process in the trilogy, quality improvement. In effect, it was seen that the chronic waste was an opportunity for improvement, and steps were taken to make that improvement. The trilogy diagram and product deficiencies. The trilogy diagram relates to product deficiencies. The vertical scale therefore exhibits units of measure such as cost of poor quality, error rate, percent defective, service call rate, and so on. On this same scale, perfection is at 0, and what goes up is bad. The results of reducing deficiencies are to reduce the cost of poor quality, meet more delivery promises, reduce customer dissatisfaction, and so on. The trilogy diagram and product features. When the trilogy diagram is applied to product features, the vertical scale changes. Now the scale may exhibit units of measure such as millions of instructions per second, mean time between failures, percent on-time deliveries, and so on. For such diagrams, next is quality control. Quality control is a universal managerial process for conducting operations so as to provide stability, to prevent adverse change and to maintain the status quo. To maintain stability, the quality control process evaluates actual performance, compares actual performance to goals, and takes action on the difference. The term control of quality emerged early in the 20th century. The concept was to broaden the approach to achieving quality from the then prevailing after-the-fact inspection to what we now call defect prevention. For a few decades, the word control had a broad meaning which included the concept of quality planning. Then came events which narrowed the meaning of quality control. The statistical quality control movement gave the impression that quality control consisted of using statistical methods. The reliability movement claimed that quality control applied only to quality at the time of test but not during service life. In the United States, the term quality control now often has the narrow meaning defined previously. The term total quality management, TQM, is now used as the all-embracing term. In Japan, the term quality control retains a broad meaning. Their total quality control is roughly equivalent to our term total quality management. In 1997, the Union of Japanese Scientists and Engineers, JUS, adopted the term total quality management, TQM, to replace total quality control, TQC, to more closely align themselves with the more common terminology used in the rest of the world. Next is difference between quality control and quality assurance. Quality control and quality assurance have much in common. Each evaluates performance. Each compares performance to goals. Each acts on the difference. However, they also differ from each other. Quality control has as its primary purpose to maintain control. Performance is evaluated during operations, and performance is compared to goals during operations. The resulting information is received and used by the operating forces. Quality assurance's main purpose is to verify that control is being maintained. Performance is evaluated after operations, and the resulting information is provided to both the operating forces and others who have a need to know. Others may include plant, functional, or senior management, corporate staffs, regulatory bodies, customers, and the general public. Next is QC process flow. Let's discuss about quality control process flowchart. First, actual performance is measured. Data is compared with established standards. If it is okay, then product will go to next process, or else it will go for repair or rejection. If it is found not okay, problem areas are explored and solution is reached. This is called as troubleshoot. Once problem solved, then do trail run and measure the actual performance. Re-establish the standards after solution, as there may be changes in operation standards. Next is, what is problem solving? Problem: a matter or situation regarded as unwelcome or harmful and needing to be dealt with and overcome. E.g., a machine breakdown frequently while there is demand of product. Problem solving starts with mental process. Here you have to think about the real situation. Then discover the issue. Then analyze the issue. Then solve the issue. Then overcome obstacles, a solution that best resolves the issue. Next is QC approach to problem solving. The QC approach to problem solving is not to reach to improvement, which is the practice in Indian manufacturing industries. There are 6 steps to reach to improvement. First step is to understand the problem. In this step, facts are collected, and based on fact, what to attack is decided. If it is theme-based or project-based activity, the target is set in the initial stage based on requirement. Next step is brainstorming to find out maximum root cause for the effect. All possible factors are listed. Third step is analysis. In this step, root cause is established. Stratification of data is used to establish the cause, and variation with time is studied. Fourth step is to take corrective action. Solution is planned and countermeasure is implemented. Fifth stage is effect confirmation of action. Whether action taken gives desired result or not. If not, then again step 2 onwards is repeated. Sixth stage is to establish improve process, and it is incorporated in documents. People's awareness level is increased, and same is horizontally deployed in other process. The main focus of this training session is to aware participants about tools used for QC approach of problem solving. In subsequent slides, we will discuss some statistical concepts and then 7 QC tools in details. Next is PDCA cycle, systematic problem solving and Deming cycle. There are many ways of dividing the feedback loop into elements and steps. Some of them employ more than 6 elements, others employ fewer than 6. A popular example of the latter is the so-called PDCA cycle, also the Deming wheel. Plan includes choosing control subjects and setting goals. Do includes running the process. Check includes sensing and umpiring. Act includes stimulating the actuator to take corrective action. Replan and follow the cycle again. Next is benefits of systematic problem solving process. It helps avoid jumping to conclusion. Helps avoid decisions based on opinions and feeling. Helps the group in focusing their attention. It provides a logic for remedies. Sets a platform to involve all concerned. Makes implementation simple. Next is why statistics or importance of statistics in quality. It is more economic to assess a sample of product and use the result to predict the properties of the whole lot. It leads to predictions with a high degree of precision. As per population sample model. From the base population, take few sample, record the sample data, study the data based on requirement, then decide whether the sample is okay or not. Accordingly, base population okay not okay decision will be taken. Next is what is statistical quality control, (SQC). When a quality control system uses statistical techniques for inspection, Testing and analysis to control quality or to conclude whether the quality of product is satisfying the customer needs or to solve quality problems. SQC is systematic as compared to guesswork and avoids personal bias and poor judgments. Next is benefits of statistical quality control, SQC. Efficiency. It helps in rapid and efficient inspection at a minimum cost. Reduction of scrap. SPC tells the causes of excessive variation in manufacturing and tells about potential non-conformance. Adherence to specification. Due to SPC, specifications can be accurately predicted and controlled. Increases output. Due to SPC, reduction in wastages, effective utilization of resources can be possible. Awareness. It creating awareness in organization. Next is basic statistical concepts. First is variation. So what is variation? Concept of variation states that no two items will be perfectly identical even if extreme care is taken to make them identical in some respect. Variation by nature is constant. There are no two things which be identical. Means no 0-0 matching. Statistical data can be characterized as variable data and attribute data. Next is what is variable data? When a record is made of an actual measured quality characteristic, such as a dimension expressed in hundredths of mm, the quality is said to be expressed in variables. It is also known as continuous data, i.e. data which can be measurable and can assume any value over some interval. Examples: dimension of a part measured, temperature in degrees centigrade, weight in kg, etc. Next is what is attribute data? When a record shows only the number of articles conforming and the no of articles failing to conform to any specified requirements. It is also known as discrete data, i.e. data which can be measurable and can assume certain distinct values, integer values. Examples: the no of defective pieces found in a sample, cracks in Next is what is mean? The arithmetic average is known as mean. Mean is nothing but the average of the given set of values. It measures the central tendency of a set of data. Mean is the average of the given numbers and is calculated by dividing the sum of given numbers by the total number of numbers. Formula for mean is mean x bar sum of all number which will be derived by total number count. Next is see an example for mean calculation. The marks of 9 students in a geography test that had a maximum possible mark of 50 are given below. 47, 35, 37, 32, 38, 39, 36, 34, 35. Find out mean of score obtained. So mean is equal to sum of all number. Total numbers are 9. So sum of number is 333, which should be divided by 9. So mean is equal to 37. Next is what is median? The median of a set of data values is the middle value of the data set when it has been arranged in ascending order, smallest to largest. If number of data is odd, then median is middle value. If number of data is even, then median is average of middle values. Next is see an example for median calculation. The marks of 9 students in a geography test that had a maximum possible mark of 50 are given below. 47, 35, 37, 32, 38, 39, 36, 34, 35. Find out median of score obtained. Next is, what is mode? The mode of a set of data values is the value that occurs most often. For example, there are 12 numbers given in a question. Here 2 presents 2 times, number 3 presents 5 times, 4 present 1 time, 5 presents 2 times, 6 present 1 time, 7 present 1 time. So maximum time number 3 present 5 times. So mode is 3. Next is pros and cons of mean, median and mode. Mean, median and mode are 3 different measures of central tendency used in statistics. Each has its own advantages and disadvantages, and they are useful in different contexts. Here are the pros and cons of each. Mean. What are pros of mean? Sensitivity to all data points. The mean takes into account every data point, which can provide a precise estimate of the average. Mathematical properties. The mean is often used in statistical calculations and has certain mathematical properties that make it suitable for various statistical analyses. Mean gives very true picture of central value in case of symmetrically or normally distributed data. As majority of distributions are symmetrical, mean becomes the most widely used measure of central tendency in any industrial or non-industrial setup. Example: mean height, weight, pressure, score, etc. What are cons of mean? Susceptible to outliers, extreme values, outliers can greatly influence the mean, leading to a skewed representation of the data. May not be representative. In skewed distributions, the mean may not accurately represent the central tendency. Median. What are pros of median? Robust to outliers, the median is not influenced by outliers, making it a good choice when dealing with data containing extreme values. Represents the central position. The median represents the middle value when data is sorted, providing a clear indication of the central position. Consider the income distribution in a country in which income of 20% rich people is roughly equal to income of 80% remaining people. In this case, mean income will not give a true picture as it will get jacked up due to high income of 20% people. Median will give typical income that will be more realistic. What are cons of median? Ignores specific values. The median doesn't consider every data point, making it less sensitive to the exact values. Limited for certain analyses. In some statistical analyses, using the median may not be appropriate or may reduce the accuracy of results. Then mode. What are pros of mode? Easy to understand. The mode represents the most frequently occurring value in a dataset, making it straightforward and easy to understand. Applicable to categorical data. The mode can be used for nominal and categorical data, not just numerical data. Mode is most easily understandable and quickly visible. Many decisions in day-to-day life is taken on modal concept. Like going to watch a movie where most people are going, or choosing color of car as the one most people are buying. What are cons of mode? May not exist or be uninformative. Some datasets have no mode or multiple modes, which can make the mode uninformative. Real-life examples of mean. Here are some real-life examples of how the mean is used in various contexts. Grades in a classroom. The mean grade of a class on a test or exam can provide an idea of the overall performance of the students. Next, income levels. The mean income in a particular region or country is used to describe the average earning of the population. Next, temperature. The mean temperature in a city over a year or a month can provide an understanding of the typical weather conditions. Next, product reviews. On e-commerce websites, the mean rating of a product provides an overall assessment of its quality as rated by customers. Next, sporting statistics. In sports, the mean can be used to describe average points scored by a team or the average performance of an athlete over a season. Next, height of a population. The mean height of a population sample helps understands the typical height of individuals within that group. Next, test scores. In educational testing, the mean score on a standardized test can show the average performance of students who took the test. Next, stock market returns. The mean return on investment for a particular stock or portfolio can help investors gauge the expected return. It is also used in astronomy. Astronomers may use the mean distance between celestial objects or the mean brightness of stars in their observations. Next, mean is used in manufacturing. In quality control, the mean measurement of a product's dimensions can be used to check if it meets the desired specifications. These examples demonstrate the wide range of applications for the mean as a summary statistic, providing a useful way to describe central tendencies in various fields and situations. Next is real-life examples of median. Here are some real-life examples of how the median is used in different contexts. Household income. The median income of a group of households is the income level at which exactly half of the households earn more and half earn less. It's often used to describe the typical earning of a population. Housing prices. In real estate, the median home price is the price at which half of the homes are more expensive and half are less expensive, providing an understanding of the typical cost of homes in an area. Salary negotiations. When negotiating salaries, the median salary for a specific job or role can help candidates determine a fair and representative income expectation. Healthcare. In medical research, the median time it takes for patients to recover from a particular illness can help understand the typical recovery period. Age distribution. The median age in a population provides insight into the age that divides the population into two equal halves, indicating the typical age of individuals. Exam scores. In education, the median exam score can show the middle performance of a group of students, which may be less affected by outliers than the mean. Car prices. The median price for a certain make and model of a car can indicate the typical cost of that car, helping consumers make informed decisions. Travel times. The median travel time between two locations on a daily commute can provide a realistic expectation for the typical duration of the journey. Loan approval. Lenders may use the median credit score to determine the typical creditworthiness of applicants. Waiting times. In healthcare settings, the median waiting time for patients in a hospital's emergency room can represent the typical time patients spend waiting for care. These examples illustrate how the median is a useful statistic for describing the middle value or typical observations in various real-life scenarios, particularly when the data distribution is skewed or contains outliers that might affect the mean. Next is real-life examples of mode. The mode in statistics is the value that appears most frequently in a dataset. It represents the most common or popular value. Here are some real-life examples of how the mode is used in different contexts. Clothing sizes. In a clothing store, the mode of clothing sizes sold may indicate the most popular size among customers, helping in stock management. Bus routes, the mode of bus arrival times at a particular bus stop can help commuters predict when the most frequent buses are likely to arrive. Telephone area codes, in a given region. The mode area code for phone numbers may indicate the most common area code used by residents. Product sales, the mode of product sales can help businesses identify their best-selling items and make informed inventory decisions. Traffic flow, the mode travel speed on a highway during rush hour can show the most common speed at which vehicles are traveling. Music playlists, the mode song in a music playlist is the one that appears most frequently, reflecting the user's favorite or most frequently played track. Restaurant orders, the mode of menu items ordered by customers can help restaurants understand which dishes are most popular. Exam questions, in education, the mode question on a test may indicate the most commonly answered question by students. Home features, the mode of features in homes sold in a certain area can help real estate agents understand what homebuyers prefer. Library books, the mode book in a library's collection may indicate the most frequently borrowed book, reflecting its popularity. Temperature settings, in a household or office, the mode thermostat setting for heating or cooling may represent the preferred comfort level. Favorite color, in surveys, the mode color chosen by respondents can indicate the most popular color among a group of people. These examples highlight how the mode is used to identify the most common or preferred choices or values in various. Next is, what is measures of dispersion? Dispersion, the extent to which the data is scattered about the zone of central tendency, is known as dispersion or variation. Dispersion or variability. Range, denoted by R, variance, denoted by V, standard deviation, denoted by sigma or S. Next is, what is range? Range is the simplest of dispersion in a sample. It is used in control chart. It is the difference between the largest and the smallest observations. The equation for computing the range is R maximum value observation minus minimum value observation. See the example. In this data set, maximum value is 121 and minimum value is 3. So range is equal to 121 minus 3. So result is 118. Like this you can calculate range. Next is, what is deviation? It is the distance between observations and the mean or average. Next is, what is variation? Variation means the square of average distance between observations and the mean, or square of the standard deviation. In the context of statistical process control (SPC), variance refers to a measure of the dispersion or variability of a set of data points within a process. It is a fundamental statistical concept used to understand and control variation in processes to ensure product or service quality. Variance is often used in conjunction with other statistical metrics like mean, standard deviation, and range to analyze and improve processes. Variance quantifies how much individual data points in a dataset differ from the mean average of that dataset. A higher variance indicates that the data points are more spread out from the mean, while a lower variance suggests that the data points are closer to the mean. In the context of SPC, the goal is often to minimize variance to achieve a more consistent and predictable process. There are two common types of variance in SPC. One is population variance, Sigma square. This represents the variance of an entire population of data points. It is calculated using the formula, where sigma square is the population variance. This symbol represents the sum of xi represents individual data points. Mu is the population mean or average. Capital N is the total number of data points in the population. Second is sample variance, S square. In practice, it is often not feasible to collect data from an entire population, so samples are used. Sample variance estimates the population variance based on a sample of data. It is calculated using a similar formula, where small s square is the sample variance. This symbol represents the sum of xi represents individual data points. X bar is the sample mean average. Small n is the sample size. Understanding and monitoring variance in a process is essential in SPC. When variance increases, it can signal that the process is becoming less predictable and may produce products or services with more defects. Reducing variance is a key objective in quality improvement efforts and process control to ensure consistent and high-quality results. Various SPC tools and techniques, such as control charts, analysis of variance, ANOVA, and process capability analysis, can be used to assess and manage variance in different types of processes. Thanks for watching this video. Don't forget to subscribe our channel to get notification about our new training videos.